So today we are here to discuss about building highly scalable Postgres platforms. So before I begin this topic, I would want to definitely make sure that we are going to cover a lot of internals of Postgres and also some of the tuning internals and also about how high availability works and some of the automations around that. Right? So, who am I? So, I am Avinash Vallarapu. People call me Avi, and so I am one of the founders of this company called Hexa Cluster. And so, just going back to the history, I've worked as an Oracle DBA in the past. I started, I think, as an Oracle DBA in 2005, and since then, I've worked on various different types of databases and authored a few books on Postgres and also created the Postgres practice at Percona. And then after which I also created a company. So this company is majorly about migrations to Postgres, majorly from commercial databases. So as part of this process, we'll also be talking about extensions in Postgres, but I got an opportunity to contribute to a lot of extensions through my work and our team, wherein we have contributed to a lot of Oracle compatibility, SQL Server compatibility, and some of these extensions which really give even performance insights, observability, and maintenance. So, with respect to a lot of functionalities, for example, there is one of these interesting extensions called CredCheck, which is also onboarded now by Microsoft Azure, and it can be used for the Azure database Postgres as well. So what is that extension as an example? So that extension is about enabling certain user and password rules in Postgres, right? So for example, in Postgres, you can directly create users and passwords. Assign any password, but there are no strict rules that we are assigning. There are some of these interesting requirements are required at an enterprise level, especially when we are building secure databases, and every organization has different practices. So, in order to make sure some of this is possible, we built that extension. So, similarly, there are many other extensions that we have created, but I'm going to talk about that. And so ultimately, we will try to do the best in understanding a lot of Postgres internals and also the tuning that matters. And also, how do we ensure that we build scalable but also highly available platforms? And at the same time, how do we handle massive a number of applications, putting not just the throughput, but also in terms of the volume of transactions being really hyperactive? How do we scale such applications? And also, how do we make sure that it works? Right? So that's what we'll try to make sure we address. And at the same time, one of the things that we need to understand is scaling in database is not just magic, right? So, okay, now I want you to scale no matter what. Database does not know what to do, right? Yeah, so now I think we are talking about AI DBA, and probably you connect your database to Claude and ask it to tune. Probably it could drop some tables, or it could say, yeah, I am finding it amazing when there is no data, right? So again, just a joke. So, but yeah, so I don't think that we are still in that stage where we probably will be at some point, right? Where we give some restrictions and make AI do some of these things, but it's still important that we understand how do we scale from performance perspective, from infrastructure perspective, and at the same time from tooling perspective. So you start with probably tuning the application layer. So at the application layer, the best that a database engineer could probably look at, or from design perspective, when speaking to a database, right, the application team could look at how the connections are handling. Do we have proper connection pooling. That's one of the important fundamentals for Postgres. While not every application might need to have that, it's important though, right? So and tuning, replication, failover automation, because now I see that Postgres is just growing, expanding, and you do not want to have those late 1 a.m. calls to automate, to answer and say like, okay, let me just do a failover because this database is not available. It has to be automatic, and at the same time application routing to load balance and scale, and at the same time even observability, getting insights into what's going on. So we will first start with the architecture and MVCC, and then we'll also talk about connections, limits, connection poolers, and some of the important tuning that we have to do, replication, and also how do we design a system which can protect itself from the failures, and also about some of the HA tools, majorly Petroni, and then load balancers, and ultimately observability. So we'll try to cover all of these as much as possible, and we'll make sure that I hope we will make it a little more interactive to ensure, yeah, it doesn't make us tired. So let's talk about architecture and MVCC. So MVCC in Postgres is slightly different from several other databases. So what is MVCC, right? So MVCC is basically multi-version concurrency control, right? So it's about so if you talk about Oracle or MySQL or SQL Server, technically there is a separate area for undo management. So before I proceed further, in this room I just wanted to understand, are you all from the MySQL background or both MySQL and Postgres? Okay. And at the same time, so anybody is from the Oracle background or SQL Server? Okay, that's great. Good. Okay, so I'll try to jump between all the terminologies. So yeah, so the way MVCC works in Postgres is slightly different from Oracle as well as other databases, and for that reason you have a lot of background workers that needs to do some of the activities, but that's not something that's specific to Postgres only. It has got its own advantages, and at the same time, I wouldn't say the disadvantages, but it's about you need to know how to optimize Postgres considering the MVCC design in Postgres. So let's start with the process architecture to begin with. So at the highest level, right? So in Oracle, you have a listener as an example, right? So similarly, you have a postmaster. So in Oracle, you also have a listener and a process PMON, which is a process monitor. That's basically monitoring, and at the same time SMON. So technically, postmaster, if in case I speak about Oracle, it is taking the responsibility of listener, PMON, SMON, a lot of these background processes that are handling the crash recovery as well as starting a process or forking a process, right? Similar to Oracle, Postgres is a process-based architecture. MySQL is a thread-based, right? So every connection is a thread in MySQL. Similarly in SQL Server. But in Oracle and Postgres, every database connection is a process. So it is the postmaster that is the parent process which is performing this fork of a process and creating a new process for every new connection, right? So in Linux, technically speaking, the more processes you create, you start a process, you stop a process, right? So that is also going to have its own overhead. So, but yeah, we'll talk about that as well. So every connection is a process similar to some other databases like Oracle. As an example, you have background writer, wall writer, checkpointer, auto vacuum, archiver. So again, there are many of these background processes that are making the database up and running, right? And perform the actions. As an example, you have let's say the wall sender, wall receiver, right? The easiest process to talk about. So the wall sender and wall receiver process is responsible for replicating one of the Postgres databases to the standby as an example, right? So wall sender sends the wall segments. What's a wall? A wall is a write-ahead log in Postgres, which is similar to the bin log a little bit, I could say, or rather, the it's bin log is a very easy way to say, but probably I can compare it to Oracle redo log, right? So these are the transaction logs, or which are sent by the wall sender process, and it's a wall receiver process on the standby that is receiving it. So there is a wall receiver. There is also, there are many other processes with respect to replication. So similarly, there is a logger process, there is a stats collector, right? So most of these processes have got different functionality. So let's actually go a little bit more into these processes, because I would say that with respect to these processes or background processes, there is some amount of tuning that we still have to do, because not everybody. So when you ask a DBA to see if there is an opportunity for tuning, there are a certain defined list of parameters that a DBA looks at and says, okay, this is optimized, that is optimized. Or probably you put it on some kind of a web and say, like, I want to optimize these parameters. How do I do that? Yeah, there are some default recommendations that can be provided, but not everybody really looks at from the point of background processes. So understanding the real role of a BG writer, the wall writer, the checkpointer. So some of these are actually creating impact on the IO. Some of these are actually creating the impact on the throughput of commits. So BG writer is the process that writes or flushes dirty data blocks to disk. For example, you have a lot of changes that are happening in memory. Everything is in memory, and a commit as part of the asset property, right? The database is said to be supporting the asset only when the transactions are durable. So the durability is achieved through write-ahead logs. So at the same time, any change that is happening in memory, right, is also written by wall writer background process to wall segments on the disk. So um, these are important again for I would say crash recovery, at the same time, even flushing the changes to the disk. So both BG writer and wall writer take similar responsibilities. And checkpointer process is again something that is going to run checkpoints. It's simple to say, but what's a checkpoint, right? So some of the internals of checkpoint is very important to understand. So as an example, the role of a checkpoint is to make sure that since the last checkpoint time until now, whatever are the wall segments that have been generated, in a simple way, if I explain it, right, very simple way, are all of those flushed to the disk? And at the same time, can I go ahead and remove some of these wall segments that have no use with respect to the recovery, or maybe replication slots, or several other reasons? But there is one of the interesting things with respect to tuning that I want to talk about, right? Instead of going too deeper into the checkpointer uh, complex reasoning. So that is when a checkpoint happens, let's say it happened at 10 a.m. in the morning, the very next immediate change to a table, it could be an update or a delete as an example, right? So where is that happening? So let's say there is a table. So maybe I can try to show. Okay, so what is a table? Technically, a table is a file in the file system. Everybody understands that, right? So if I say, for example, show data underscore directory, okay, and so this is the data directory, right? Oh, I'm not sharing that. Okay. Ooh, okay. Let me just skip and show. Okay. Okay. Good. Excellent. Thank you. All right, so this is a data directory in this case. It's a Postgres version 18. So I'll say show data underscore directory, right? This is a data directory. So let me also say, so I'm going to make it a little more easy, and I'm going to start also explaining you some of the views that I'm looking at. So pgstat database is one of the interesting view using which I can get the database ID and database name from pgstat database, right? So you have the default template database and the Postgres database, right? Okay, so now let me also go ahead and try creating, okay, maybe I have some tables. Okay, I can try to say pgbench -i -s10, and I'll use pgbench to, okay, just a second. Yeah, I'm connecting to the standby instance. Okay, understood. Let me just connect for a second to the other instance. Just a second. I found a way to hide my screen. So, okay, now you don't see me what I'm doing. Okay, good. So, okay, so I'm just connecting to the other instance, and okay, or the easiest way that I probably would do this is, yeah, let me actually do something interesting in this case. I always complicate my demos. So what I'm doing is, because it's not a yeah, so pg3 is my uh, primary, right? So because I'm using Petroni to set up this primary cluster, just in the interest of time, I'm going to go ahead and do a switchover. Okay, so yes, that's right. pg3 is the primary, correct? And pg1, I want pg1 to be, yes, just do it now. Okay, yes, please go ahead. Yes. So what I'm doing is I'm doing a failover or a switchover, right? So I'm making pg1 the primary just because I want to run the command in the server that I'm connected to. So yeah, I don't think we would do that in reality, right? So, okay. So let me just go ahead and say, yeah, okay, the leader is running. So let me now run a pgbench. Okay, so it's running pgbench to create some tables, right? And also, yeah, okay, so some tables are created. Now, where are these tables created, right? What are these tables? What is a table in reality, right? So when you see the tables created, ultimately, if I remember correctly, right? So there is a function called pg relation underscore file underscore path. Yes, file path, sorry. Yes. Okay, and you give the table name, right? Now it says that in the base directory, right? So inside the data directory, okay, so this is the data directory location. Inside this data directory location, we have a base directory, and inside the base directory, we have another directory called 5. What is that? We saw that here already. 5 is nothing but the database ID, right? So that ID is the name of the, basically that points to the Postgres database in the background. So in that directory, there is a file that got created. So let me just take a look at it maybe. So I'll say ls-larth, okay, and I'll say base, okay. So there's a file, it's 129 megabytes now, right? So what happens when you create a new table? I'll say create table, okay. I'll say my table ID int, okay. Now what is the, oh, okay, so I can go ahead and say something like, let me just complicate this query a little bit so that you know what all I'm joining. So maybe I'll say okay, from pg underscore class. So pg class is basically a catalog table that contains the information of all the objects not all the objects, but some of the objects like tables, sequences, views, and indexes in the database, including the parent partitions as well as the child partition tables. And then pg underscore namespace consists of, basically namespace is nothing but the schema, right? So I'm going to say select, okay, pc.oid comma pc.rel name, if yeah, rel name, and I'm also going to put maybe pn.nsp name comma, okay, yeah, from, okay, where pn.nsp name equal to public, we created in the default public schema, and I'll say pc.rel name equal to, let's say, this table that I just created. Yes, okay, good, very good. Okay, so I said join on, right? Okay, sorry, on, and I'm going to say pc.rel namespace equal to pn.oid. Yes, is that correct? Okay, pc, I removed the c, sorry about this. Okay, so this is the OID. I can simply get it using rig class also, but I complicated it just to even present that. Okay, there is PG class, there is PG namespace, some of these catalogs that is what is happening internally, right? I mean, I can also do some of the other information is available when I do a /dt plus, such as size and etc. Right? Okay. Now let me go ahead and do a similar file path, relation file path of my table. So when I do that, okay, just a second. Oh. Okay, you see the base directory and the file that got created. So what would be the size of this file? I just created this table, right? So the file size is basically 0. There's an empty table that just got created. Now let me do one thing interesting. I'll say insert into my table values 1, right? It's just a table with one record, if I understand. I'm sorry, one column, because that's how I created it, right? Yeah, only one column. Okay, good. Now what would be the size of this file? You see, 8 kilobyte, right? So if you say show block underscore size 8 kilobytes, so you can just do something like select name comma setting comma unit from pg underscore settings, where name equal to, let's say, block underscore size, right? Okay, so it is yeah, it's not displaying the unit, so but yeah, so this is the block size in bytes. So what it means is every time Postgres assigns an 8 kilobyte block, every time it needs to. So for example, if there is a table to which you are inserting data, right, it is assigning 8 KB blocks. So now I was talking about checkpoint, right? I'm sorry, I said a lot of things just to talk about checkpoint, but it's very important. So what happens in this case is whenever an update or a delete happens to a table, at the under the hood, it is happening on that page or the block, right? So what's happening is that block is fetched to shared buffers, which is the memory area of Postgres, and that, I mean, we call it a dirty block, right? So the block is modified, and then technically speaking, we assume that only that changed vector is actually returned to the transaction log, but no, the entire 8 kilobyte block is written to the wall segment, right? So right after the checkpoint, every first change to a block is always a full page write. Okay, so this is a concept that we have to now think, okay, now how can I avoid it? So the way to avoid it is, I mean, when do you want to avoid it? Especially when you have too many wall segments that are being generated, right? So you do not really want that to happen. So, okay, what happened? Just a second. Yeah, okay. So now in this case, if you say show checkpoint underscore timeout, see the default checkpoint timeout is 5 minutes. So what it means is we are letting so many full page writes happen because every 5 minutes a checkpoint is triggered. And if it's, especially if that's an update intensive table, right? Or a table which has also got deletes that are continuously happening, then you are really forcing a full page write even more often. So for that reason, you have a very heavy growing wall segment. So you are really writing too much to the wall, to the directory that actually contains a wall segment. So even if you want to optimize that directory, or you want to point the transaction logs or the write ahead logs to another disk, even then you are not trying to get the best throughput. So increasing it to 15 minutes, 30 minutes, 1 hour is fantastic in some cases. But at the same time, we also need to understand, because the checkpoint frequency is getting increased, or not increased, decreased, the frequency is decreasing, but the checkpoint is happening at a larger interval now. Whenever a crash happens, if the database comes back up, it has to replay all of these committed changes for that period of 30 minutes or 45 minutes, depending on your checkpoint. That's the only drawback, right? But that is still reasonable. Performance is definitely one of the important factors that you might want to look at, right? There is another thing that you can actually do, right? Currently, full page writes defaults to on. So in the previous versions, you probably see full page write set to off. So, full page writes is actually always on, right? Sorry. I meant to say wall compression. I'm so sorry. Yeah, wall compression. So what is wall compression? You see the full page writes set to on. So in this case, what's happening there is wall compression is disabled. So this entire 8 KB block that is written to the wall segment is not compressed. So with wall compression set to on, we can compress that full page at least. So that way, the size of wall segments probably can be completely reduced. So let me interestingly try to show you. It is using something like that, right? Like some kind of a gzip internally. But let me actually show you maybe something interesting. So one of the benchmarks that I published when I actually was at Percona, right? So, okay. Yes, okay. So sysbench tuning, I'm going to Postgres. Let me just stop the show and say Avinash Vallarapu, Percona, something like that, right? So yeah, this was one of the you read that? Okay. Yeah, this is something that I have written, right, in 2018 though. So you have to definitely change this. But what I wanted to talk about in this case is the wall compression. Okay. So here you could see that for the workload, walls produced 3.3 terabytes of walls have been produced. With wall compression to on, we were able to reduce it down to 1.9 terabyte as an example, right? The total wall generation, right, in that 10-hour interval as an example. This was a 10-hour benchmark. So wall compression can help, undoubtedly, right? So this is at the cost of CPU, absolutely. Absolutely, yes. So it can, it depends on the infra, yes, that's right. So auto vacuum is again another background process. So auto vacuum takes care of a lot of things, right? It's not just a vacuum. What is a vacuum? We're going to talk about that in detail. But auto vacuum is something that is responsible for launching the workers that are performing some background tasks, not just vacuum, but also analyze. Okay, so we're going to talk about that. Archiver, so just like archiving in Oracle, right? So you have transaction logs, which are write-ahead logs that are written to the wall segment, wall directory, and those walls are archived to a permanent storage where you have your own retentions, right? Using the archiver process. So archiver process just runs a script or a command that you pass to the archive command parameter. And then you also have logger process, which is responsible for logging all the messages. For example, you will have a certain set of configurations that you could do about what you want to log and at what level do you want to log. For example, log every query, just like slow query logging in MySQL, right? You also have a similar slow query logging, right, in Postgres. And when you enable that, the logger process says, okay, now I need to start logging even this, right? So it decides what to log in addition to errors or debug messages based on our configurations. And the stats collector, this is a very, very misunderstood background process. So stats collector, the name, it says that yes, it's collecting statistics, but when we come from probably the Oracle world or maybe even the MySQL world, we say that, okay, maybe this is responsible for collecting statistics or gathering statistics. Okay, up to what level? So what stats collector is actually doing is it is looking at the type of changes that are happening and tracking the changes since the last analyze. So analyze is the actual background activity that is happening as part of the auto vacuum process. So in MySQL as well, you have analyze, right? So you similarly have, gather stats in Oracle, right? So this is responsible for collecting some histogram boundaries as well as understanding the most common values for a column. What is the data type? What is the precision and length, and the observed averages, and depending on the histogram boundaries you choose, it's going to collect some statistics and store the statistics so that it can be leveraged by the optimizer or the planner, right? So the planner of Postgres decides the execution plan based on the statistics. So stats collector is helping the background process, which is auto vacuum, decide when to run that analyze, right? So it is not collecting, but it is helping the auto vacuum launcher and saying, since the last time you have actually run the stats, so many changes have happened. So see if my table is a candidate for the next maintenance, right? So how does Postgres know, or the auto vacuum launcher know when to run vacuum, when to run analyze on a table? It is the stats collector process, right? And in order to also optimize the stats collector, there are some of the things that we need to actually do, understand, right? And wall sender, wall receiver, we already discussed about that. Now, oh my God, we have 88 slides. Okay, and 40 minutes, good. Okay, so one process per connection. So we have a single postmaster, we already discussed about that, and the default is 5432, the port, right? And at the same time, you have a new connection for each process. We already discussed about that, and that's forked by postmaster. So if you go ahead and establish a connection to the database, you see a process in the background, right? And so for example, if you say ps-eaf grep Postgres, right? So I was talking about these background processes: wall writer, auto vacuum launcher, checkpointer. Yeah, so this again, this is something interesting which we will probably talk about. So as you could see, the postmaster, which is the parent Postgres process, right, is running with process ID 8467, right? And as you could see, for all of these background processes, right, 8467 is a parent process that forked this process. So all the background processes are forked, including our database connection. So if I duplicate this terminal and run a connection, right? I mean, and create a connection, you see that new process appearing here with 8467 as the parent process, right? So it is doing that fork system call. Okay, so shared memory. So in the memory, you have shared buffers, wall buffers, and lock manager, and a lot of other things. So that's maintained, and background processes, we spoke about that. Yeah, startup process is another process that is actually responsible for the real replication. So it is a startup process which is actually replaying all the events on the standby. Wall receiver is used as one of the channels to retrieve the wall records, but it's a startup process which is actually doing a good amount of activity on the standby. Okay, so like we already discussed, Postmaster takes care of supervision. If any process dies, it is responsible for spawning, again, recreating that background process. And if I go ahead and kill the auto vacuum process now, Postmaster might decide to crash completely, like the Postgres instance, or it might just go ahead and start the auto vacuum launcher process again. So that's what it does, right? And then at the same time, it's not multi-threaded, it's multi-process like we discussed, right? So yeah, a very bad example of a restaurant analogy. So Postmaster is a host, and the backends are the dedicated waiters, and the kitchen staff for the background work as well. I think what I explained probably is more easier than looking at that example, right? So, okay, yeah, good. Okay, yes. No, I think no one can agree on why or how current methods work so well. Yeah, yeah. There are similarly multiple. In the past, somebody has rewritten the entire Postgres code in C++ also, right? So, and the problem is the community recognition. So, as a single author projects, or probably a single company attempting to do that with 2 developers or 5 developers, I've seen similar things happening from earlier. So, but they eventually die because of the community lack of community support. So yeah, so the answer is yes. So there are many such folks that got created, but none of them unfortunately could make it. So there are even interesting storage engines that got created to bypass the MVCC, the way MVCC works in Postgres today, to go past that and try to rather have the undo mechanism similar to, like how you have in MySQL as well as InnoDB and Oracle or SQL Server. So some design was put in place. Z-heap storage engine was again something that, so there was pretty good amount of activity that actually happened. Too many contributors came in, and ultimately that's gone, right? So yeah, so a lot of things have been attempted, but yeah, yeah. No, great. Thanks for asking that. So yeah. So we have shared buffers, right? So which is basically um, uh, the shared memory. So as we discussed, any change that happens to a table or any change in the database, it happens in shared buffers. So the data blocks are loaded from the disk to the buffers, and then the changes happen. So optimizing shared buffers is also very important, right? So for example, in Postgres you actually find double buffering, right? So what is this double buffering? So when a connection gets established. Let's say an application is requesting for retrieving certain records from a table. Now you're doing that select statement, you're running that, the execution plan is prepared, it gets those data blocks from the disk, loads to shared buffer. So this is what we see it. But internally what's actually happening is Postgres is giving that work to operating system and stating that get me those data blocks or pages from the disk. Now it is the OS which is loading those blocks if they are already not found in memory, of course, right? So if they're loading them to the OS cache, and from there you see a memory copy, which is ultra fast in general, right? I mean, that's negligible, but so that is what is happening. So for this reason, do you want to give a 50% to shared buffers and 50% to OS cache, or you give a significant portion like 25% to shared buffers and 75% to OS cache? Leave that. So what happens is the amount of cache that can be maintained for a database can actually be more if you are giving more room for the OS cache, right? Unless you can fit your entire database or your the active data set, we call it, in memory. So if your active data set, the data set on which all the changes or all the activity reads and writes happen, let's say that's only the past 1 day always, right? Or it's a stale or a static database which is not really changing, but you have a certain volume of data which is always read. So how much memory is required to load that? Let's say all of that can be fit in shared buffers if you set shared buffers to 80%. Fantastic, right? So this is what we need to understand, but how do you optimize it? So in order to see this information, you need to understand how many pages or data blocks are going through shared buffers hit, and how many data blocks are going through read, and how many read means basically there is a memory copy probably happening from OS cache to shared buffers, and then how many are actually being read rather from the disk. So you need to basically do a math. Based on that, you need to assign shared buffers certain values. So we're going to look at that, but this is one of the important as long as we understand that this is what is happening at the higher layer, right, where there is a memory copy, there is a double buffering, that's when we know, okay, let's understand the active data set, let's see how we optimize and give more memory to shared buffers or OS cache. And then how do you tune? So you want to make sure that when you assign shared buffers certain value, you also look at not just the OS cache, but also there are certain other parameters that are also going to utilize memory. Work mem, probably one of the memory parameters you might have heard about, right? Work mem is basically the sort memory area, right? So yeah, oh, you have it here. Okay. So work mem is basically the sort memory. To keep it simple, let's say you're running a select star from table where employee ID less than 10, order by let's say age, right? And then you are basically retrieving the results in one order, which is based on the collation and a lot of other locale settings, etc. But I mean the collation technically, right, which is deciding all these order, but after that you're changing that sort order. So now there should be a transient stage or a temporary stage to hold the records that are retrieved before they are sorted, so they are later sorted. Now this is basically the memory area that we are talking about with respect to work mem, and it's not just about order by, so there are many other reasons why work mem comes into picture. But assume that you have a large table, you're reading a lot of rows, and now if you look at the Postgres execution plan, for some of the queries, you see it's writing some temp to disk, but not doing a sort in memory. So this is when we realize that, okay, so that sort memory, which is work mem, is not able to fit the result set before it sorts. So it's writing all of that rather to a disk, which is the temp buffers. So this is when we want to go ahead and see if we want to tune the work mem, right? But do you want to set work mem globally to 1 gigabytes across the entire instance? What happens? What happens is, yeah, you probably will be able to use the database, but I hope, because if you have 100 connections concurrently connecting to the database and running some interesting queries which are always utilizing some sort memory, you are over allocating the memory, and there is also possibility of parallel sort operations. So in Postgres decides that depending on your parallel workers and the configuration. So in this case, it's important to understand where do we need to tune. Firstly, when there is such a requirement, can I optimize the query? Is there a way to redesign the query so that I can do some interesting joins with which, if for example, I'm sorting everything, somehow I see that the Postgres is actually sorting everything much upfront and then putting certain conditions to filter that data because of some other joins. Let's say Postgres is taking interesting bad routes. Can I rewrite the query to help Postgres do a better job, right? Or can I rather collect statistics in slightly different way, because statistics can actually be collected in many ways. It's not just about the default way of running the analyze, but you also have different type of statistics that you can collect with different combinations, so that you will be able to give even more details to Postgres. So we need to take a look at that, and ultimately when we know that, yeah, I give up, this is how the workload is, we will need to go back, sit with the application team and say, okay, we can set session level work mem. So we can say set, probably application can say set work mem to 1 GB only for this specific process at the application layer. So it's very important to have that fine-grained control on work mem instead of just going ahead and setting work mem as 64 MB, 128 MB. Yeah, that may be okay with the current architect, current kind of systems we have. Nobody cares about RAM and CPU anymore unless you're on cloud. But yeah, so so now you need to basically look at the worst case peak. So if you set it to 256 megabytes as an example, you need to look at the worst case peak depending on the max connections that you have. So max connections, the default is 100. So at a given point of time, there can be 100 concurrent connections that can get established. That's what you're allowing. Of course, there are 3 super user reserved connections by default, but you are allowing 100 concurrent connections. So all 100 concurrent connections, if they utilize a work mem, let's say, for any reason because of the type of queries, the worst case is 450 gigs. So, I mean, considering 2 processes, 2 parallel work mems, etc., right? Again, we just need to see how we try to avoid that OM killer. Is work mem assigned by default, or is it only assigned when? That's right. Only when Postgres decides that it needs it, that's when it's assigned. Yes. Okay. So now, what happens in a read, right? So what happens is basically, again, this is about what happens when you run a select in a database, right? So when you run a select in a database, again, while it of course returns, I mean, it prepares the execution plan depending on the statistics and various other optimizer level parameters. It looks for specific relation and blocks in shared buffers that are estimated to contain the result set, and then this is where we rather call a shared buffer hit if it's already found in the shared buffers, which is a memory area, the ultimate memory area, which is presenting the result to the client. And if it is not found in shared buffer, so that's basically a miss, right? And that's when it is basically looking at the OS cache, and it's requesting for the it's requesting OS. Okay, I don't have it, give it to me. Now the OS is looking at it and saying, okay, I have it in the cache, let me give it to you. Or it's going and reading it from the disk. So again, this is something that we discussed a little in detail already. And even the write and commit, we already discussed that the modified a page is read to shared buffers, it's modified in memory, and then a wall record is generated, and then ultimately once it's committed, commit is ensuring that the acknowledgement from the wall writer process is also eventually received, right? So I think it is making sure that the change is also written to the wall segment on the disk, and only then a success is sent to the client. So with respect to the wall segment, it is very important to have wall segments on a faster disk. So if you, because the speed of a database or a transaction depends on the speed at which you're able to write transaction logs, right? So the least amount of transaction logs you write and the fastest throughput that you can see when you're writing to the transaction log, that decides the performance. So how do you write low volume of data to transaction logs? Tune your checkpoints and majorly tune your checkpoints, right? So that's one of the best ways to optimize the amount of changes that you're generating, and not just tuning the checkpoints. Did anybody hear about hot updates in Postgres? Heap only tuples? Yes, right? So, yeah, so this is another way to achieve interesting. So, we'll talk about vacuum and everything, and then we'll talk about that. Yeah. So, I almost cover all my future 20 slides. So, yes. Okay. So, any questions that anybody wants to ask? I know I keep going like this, but I just wanted to. Uh, Yeah, yeah. So that is definitely correct, right? So this can also become a bottleneck. So basically, the check pointer process can just hung in memory. As an example, it could be probably taking a lot of memory and taking more time to complete the checkpoint, as an example. Or so some of these can be because background writer, so shared buffers, the algorithm, which is basically the algorithm to flush all the buffers that are least recently used, because it applies that LRU algorithm. Um, we are fine there at the shared buffers level, but at the flushing changes to the data files and syncing them, yes, you will really see some kind of a latency with respect to the checkpoint, and that can definitely cause some amount of. So that is when you need to. I think I have in the coming slides about BG writer tuning. So you have to tune the background writer, but again, at least that is still a minimal challenge compared to the speed at which you can write wall. Yeah, yeah. Okay. And when you say dice away, right, Kunal? Like, what do you mean by that? Yeah, but the thing is, accumulating walls. is one. Every transaction wants to write. So accumulate them for 7,000 transactions and then flush this. That's generally faster better. And at the same time, you have your checkpoint duration as an example. So there is one of these things that I thank you for asking that. Actually, I'm going to show you this. So checkpoint completion target, right? So this is set to 0.9 as an example. What it means is if checkpoint timeout is, let's say, 5 minutes, okay? So when checkpoint starts, you have 90% of 5 minutes amount of time to flush the changes as part of the checkpointer process, as part of that checkpoint. So what it means is, let's say you set checkpoint to 1 hour, checkpoint timeout to 1 hour. So you have 90% of 1 hour, like 54 minutes to flush all those changes. So you do not, because what happens is in Postgres, if you would see, if you set default checkpoint timeout of 5 minutes, when you run some benchmarks, you'll see some spooky spikes, right? The latency spikes. Suddenly there'll be latency and then things will be normal. Suddenly again there'll be latency, and that is because the checkpointer is kicking in every 5 minutes and it has got, let's say now it's 0.9, but it used to be even lesser, the checkpoint completion target in the previous releases. So what used to happen is you have a very tiny portion amount of time to flush everything. So everything is waiting for, okay, let me just go ahead and flush everything, and it's taking all the IO and it's increasing the latency, as you said. So you have a way to spread the checkpoint activity over a larger interval. All you're doing is accumulating wall, right? So it is still, so this can be challenging, especially when you shut down Postgres. It can take time. Also take time, crash recovery as well. Yes, so those are some of the challenges, especially again these are if you are getting into the and in that case we have to also optimize the storage undoubtedly, because it is such a throughput demanding system, and if the wall segment is so many times faster than the data directory, which is actually taking all the data, and you have such a heavy activity happening which is really increasing the volume of data that needs to be part of, we really have to also make sure that we have a faster storage ultimately, right? So I think, yeah, nowadays I think NVMe and everything is becoming pretty, flash storage is pretty, yeah. Yeah, yeah, yeah. Correct. Yeah, yeah. At least we are definitely in a better state today. Yeah, these are all nice ones. Yeah. Okay. So durability. So we discussed about wall. So wall is responsible. Wall is required for crash recovery and ensuring that the changes are durable. And so we also use walls. Walls are the ones that are used for setting up high availability, right? So wall segments are streamed to the standby instance, and we replay there, and also for point in time recovery. So I'm interested, interestingly, I did some kind of a research to do the binary decoding of wall segments, which is basically what logical decoding is doing. Without connecting to the Postgres database, like offline. So you have PG wall dump as an example. That's one of the utility using which you can read the contents of a wall. So for the purpose of replication, I tried to see how I can even bypass that and go even deeper level, decode the binary reader log, the wall segment, and apply the changes, right? So yeah, I could not really achieve what streaming replication is doing ultimately. That's how it is, right? Because streaming replication is the most fastest replication, that can ever be possible, because it's doing a byte replication. It's just doing a direct storage replication. It's not really reading the changes from bin log, as an example, in MySQL, and applying that insert or delete or update, right? It is, the data block is just replicated, right? So the data block is replicated. So this way, there is no much delay that we can actually see between the primary and standby. I think I'm just talking about the replication lag that you can probably see in MySQL, especially with streaming replication. Even if you're dumping too much of data, well, it's also based on the network, but you really would not see so much of a replication lag as you see in the other systems which are not storage. Yeah, it's similar to, again, the performance of DataGuard in Oracle, right? So that's also doing a storage level. But if you're doing logical replication, that's a different story. So again, so yeah, checkpoint and background writer, like I said, a little bit of a similar activity that happens in the background, right? So the dirty buffers that are continuously generated, those are cleaned and also written directly to the data files, right? And checkpointer also dirties the buffers, but at a checkpoint timeout interval, right? And I think we discussed about the story of the full page writes as well as the 8 KB page, and how, so there is one more important point that I realized I did not mention, and that is, I discussed about every first change to a data block or a page being a full page write in the wall segment, and every subsequent change will only be recording the change vector, so it's no longer a full page write. So that is why increasing the duration of checkpoint, right, or the timeout of the checkpoint is going to be helping us, right? Okay, so did everybody look at the async IO as well as Postgres 18 talking about, now you have async IO, asynchronous IO. So okay. All right, so again, some of this work actually started in Postgres 17, which enabled Postgres 18 to really have the capability of async IO, right? So you have the new technique that you can choose, like IO method is, be it worker or IO uring or sync. So majorly, it's able to go and perform parallel read of the data instead of a sequential read, right? Asynchronously, especially helpful in the case of sequential scans or full table scans, right? So it's able to go and spawn multiple workers to go and read more data in parallel. So previously it used to be sequential. So we are able to really leverage the recent improvements with storage, right? Nowadays, like I said, storage is not a challenge, right? Okay, so we'll talk about MVCC before we probably stop for any questions. Okay, so what is MVCC in Postgres? How does it work? And this is where I want to spend some time. Okay, so MVCC stands for multi-version concurrency control. So the name speaks it, right? So when we are talking about a relational database that has to support ACID properties, right? So we are talking about the ability of readers not blocking writers, right? So what it means is readers should be able to read data as of a consistent point while writers are still modifying the data, right? For example, let's say at 10 a.m. in the morning, again, this is considering isolation levels. Isolation level, let's say set to read committed, right? You're at 10 a.m. in the morning, I'm getting the count of employees, right? Let's say it's 100 or sorry, 100,000. And now, let's say at 10:15 a.m., the number of employees increased from 1 million to, let's say, or 100,000 to, let's say, 150,000. Totally impractical. But now the count has changed. That's what I'm trying to say, right? From 10 a.m. to 10:15. But let's say that a query started at 10 a.m., which is about select count of staff from employees. And that query took 30 minutes to complete. Now, will it show the new count or the count as of the point where the query started? It should show the count as of the point when the query started, right? So if the query started at 10 a.m., it's getting us the count as of 10 a.m. Even if the query takes 30 minutes to complete, and just 15 minutes after the query got started, even if the count changed, the first query is actually giving us the result as of the point in time when the query started, right? So this is what is read consistency too, right? So how is Postgres achieving it? So what's happening is whenever any changes are happening in the background, in MySQL with InnoDB storage engine or Oracle with undo storage, every update or a delete is tracking the previous version of the row in a separate storage called undo, right? So there is an undo storage area where the past image of the row is stored. So now when you run a select, similarly in Oracle, if it's retrieving the results, it knows that it needs to get some data from undo. So there is, in Oracle, if you would have seen, or even in MySQL, you get something similar to undo not available or snapshot too old, right? This is one of the very, very interesting errors because you have a limited undo area and you do too many changes, you get this. But what Postgres does, interestingly, is it doesn't separately maintain an undo area to store the past images. It is maintaining multiple versions of the row within the same table, right? So if you delete a row or a tuple, it is not actually removing it completely. It's just marking that this row of this version has been modified by this transaction ID, right? It's internally tracking the transaction IDs that are performing some changes against the row. And now Postgres says, okay, so this version of the row is not visible to the transactions that started after this transaction ID. So anything that started before or in a range of these transaction IDs should still be able to see that row, but not the future transactions, right? So ultimately, within the same table, you have multiple versions of different rows. So that is basically the multi-version concurrency control. So the cost is that old versions can pile up, right? And this is why you need vacuum, right? What is vacuum in Postgres? Vacuum is responsible for cleanup of those older versions, right? As long as there is nothing else that's still attempting to read it, or there are no such transactions with transaction IDs that started before that record got or became a dead tuple, right? What's a dead tuple? Dead tuple is basically, or a dead version, dead row is basically a row which is an older version in a simple term, right? So how is it tracked internally? Okay. So this is where I want to show xmin and xmax, right? So we just created this table called my table, right? So we see that it has got only one column in it, but the answer is not just one column. So I can say select xmin, xmax, ctid, id from my table. So every tuple or a row has got a data structure which stores some information additionally, and that is xmin, xmax, ctid, and there are three more. So there are six such different attributes or columns that do get added as part of the heap tuple data structure. So what is xmin and xmax? Basically, these are the two columns that are helping Postgres decide whether that row should be visible to a transaction or not, right? So the row visibility is decided based on xmin and xmax. Okay, so every row version, so every time you insert a new row, there is an xmin assigned, right? And that is nothing but the transaction ID that inserted that row. So if I say, for example, let me do one thing interesting. So I'll say begin select txid transaction ID underscore current. Okay, and I'll say insert into my table values, I'll say 2, right? I'm saying commit. Now if I do the same, select xmin, you see the xmin is nothing but the transaction ID that inserted this row, right? Now if I do an update, right? Now if I do an update, what we assume is that this value is updated, right? So for example, if I say update my table set, okay, very bad way of presenting, I should have got another column. Okay. So what really happens is, even if I do that, it won't show up. But okay, so if I do an update, now what happens is another new row is inserted. So it's not the second row that is actually updated. If I go and update one of the columns of the second row, what Postgres does is it sets the xmax value to the transaction ID that did the update, right? So if in case 781 is the transaction ID that is running the update, for the current version of the row, which is with ID 2, you'll see xmax set to 781. And if we, let's say, want to update one of the columns of this table, assuming that it does exist, there is a column called name, let's say, right? If that name is updated, what happens is another new row with the actual updated value is inserted. So an update is doing a delete and an insert, both, right? So an update is no longer an update. It's not an in-place update. So Oracle is also doing something similar, but Oracle is rather inserting the previous version of that row in undo and doing an in-place update, right? And that's what even MySQL does. That's why you see sometimes when you're migrating from Oracle to Postgres, or when you're migrating from MySQL to Postgres, we kind of assume that the row pointers can be referenced in some of the queries. For example, in Oracle, the famous row ID. Row ID never changes for a row unless it's deleted. But in Postgres, just one update is sufficient. The CTID changes. What is CTID? Page 0, line item 2, item pointer 2. So CTID is basically the position of the row in the file of the table. So in a table, which is nothing but a file in the file system, it's a set of 8 kilobyte blocks. So if I just go ahead and look at the same from pgbench table as an example, I'll say pgbench accounts, right? I'll say limit 1000. Okay, sorry. Let's say, yeah, fine. So you see block ID 0, and at some point even let me just go ahead and maybe do another PG bench, right? Yeah. Correct. No. So what it does is it marks it as 781. It says xmax underscore committed. So there is one of the hint bit which is set to true. Okay. And leaves it there. So a delete is not required to insert a new row. You are updating, yes. Correct. 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 Exactly. The Xmen will be the transaction ID that did the update. Yeah, I have some slides to show. Correct, same data as well. Technically, the thing is, if you run, okay, I can do that. Okay, so I can say update my table set, okay, ID equal to 3 where ID equal to 2. Now what happens is if you run that select xmin, xmax, etc., it won't show you the ID 2 at all, because so what is your isolation set to? So one second, let me show you that. Transaction underscore isolation read committed. So you're reading only committed data. Your application, when you are running select, should it read the current versions as well as the past versions? No, even then no, because that is a future transaction compared to the past. You can. So I'm going to show you that. Yes, yes. So that is what it is. Yes. Okay. So okay, maybe I can show you that. So there is this extension called. Oh, let me just ensure here and say there is this extension called page underscore inspect. Page inspect, sorry. Okay. So page inspect is an extension that allows you to inspect inside a page and show all the past as well as the current versions of records in that page. That is when you can see it. Okay, so page inspect actually exposes some functions which you can call by pointing it to that specific page that you want to inspect, right? That's it, exactly. Yes, exactly, correct. So especially when data corruption or block corruption happens, this is one of the interesting extensions that can be leveraged. But that's yeah, that's the thing. Yes, good. This is very good. Thank you for asking again, because that is going to generate some kind of interesting thoughts in everybody, right? So it's going to connect. So I hope is everything clear so far until now what we discussed about, MVCC as well as some of the background processes and some optimizations that we have discussed until now, right? Okay. Yeah. Okay, so like I said, the easiest way to look at it is Oracle has got a separate undo area which maintains the past images until a certain amount of retention, and that retention could be based on size or could be based on time. But Postgres does not have such undo retention. It maintains that undo as multiple versions within the heap, within the tables itself, and the vacuum process only cleans those older versions when it knows that there are no such transactions which are still live active and existing from the point before those older versions were generated. So it needs to make sure that there are no such transactions that may still require a consistent image of that table as of that point, right? So yeah, heap only tuple. So this is where I think I was talking about. Okay, so we just now discussed that an update can create multiple versions of the same row. Now what it means is, in some of the systems, I've actually worked on some of the systems which are related to food delivery applications, especially during COVID. I've seen one of the companies in Europe that got its overall revenue footprint increased by 800 times. Good for their business. But what were they doing? They were using Postgres as the data store for the application. And every time the delivery driver starts, from the location, okay, now it's my next order. I need to go to the restaurant, pick that order, and deliver to the customer. Every 10 seconds, the status of the delivery driver is getting updated. There is an update that's happening. Great. That is what the developer wants to do. Yes, I want to update the status and I want to show the realistic status. I want to keep a track of the log. Okay, where was the driver 10 seconds ago? So you write that information, you send that as part of the queue to some other store. But at the same time, you're also updating the freshness so that, when you run a select, you see, okay, where is the driver? On the app, it shows up. But what's happening? Postgres does MVCC differently. Every update is generating an older version. Now, we discussed about a data block being 8 kilobytes in size. We saw that, right? So let's say you have 100 such drivers to begin with, and you have 10 drivers that can fit, let's say, in one page, 10 driver specific rows. Now, you ran an update. Now to generate a new version, you do not have a space in this data page anymore. What happens? A new data block is created, which is the 11th data block, right? Now, the new version is recorded in the 11th data block, and the older version is in the first data block. Now, because of this change, what's happening is the underlying indexes also need to start pointing to the new data block. So there is an index write that has to happen, right? It's not just the field or the column that got updated, but the entire row is moved. So if you have 10 indexes on that table, all the 10 indexes now need to be updated. And imagine that happening for thousands of drivers. This is where heap-only tuples can support. So what happens in this case is you set an interesting parameter called fill factor. The default fill factor is 100 for tables. But now when you go ahead and set, let's say, fill factor to 70% as an example, what you're trying to say is, whenever an insert is happening, insert to a page only up to 7 rows. That means fill it only up to 70%. Leave the remaining 30% for within the page updates. Okay? So within in-page updates or in-place updates. So what happens now is, when one of the delivery driver status is updated, a new version is generated within the same page, and the previous version is an older version. But there is a pointer from older version to the new version because it's within the same page. Now, that does not require an index update anymore, because index is pointing to the older version and the older version is saying go look at the new version because it's in the same page. And that is not at all a difficult performance challenge, because when you're reading, the entire data page is already in memory. You're reading block by block. Now, there is another interesting thing that happens. Okay, the older version is generated, but the vacuum has a work, right? The answer is no. Why? When you run a select, interestingly, Postgres is automatically removing this older version. And it's fixing that pointer. Right? So Postgres is writing on a select in the case of hot updates. That's one of the interesting things that is always misunderstood. Right? So it is technically performing some amount of vacuum activity, which is interesting, right? So now what's happening is, unless the column which is updated has got an index on it, right? Any other index is no longer required to be updated, right? So why do I say unless the column? Because for example, you have an index which is basically on driver status, right? Customer does not really leverage any such functionality which is looking at the driver status, because he's not looking for all the driver statuses. But probably someone sitting in the back office may wants to see based on the driver status, right? So that's not a very frequently occurring operation. But on the driver status, you have an index. Now, every time you update the driver status, the value is changing. So of course the index has to change. But other than driver status, if there are other columns, let's say on the driver ID, company ID, region ID, or something else, right? If on those columns there are indexes, those indexes need not be updated anymore, right? So for update intensive tables, there's a real game changer. So that's what we did. We went and tuned it, and all drivers were happy, right? So, okay, my app is not stuck and customers are happy. Yeah, we do not see yesterday's orders information anymore, so we see the current order, right? So yeah, so this is how we need to understand some of the semantics and internals of Postgres to define tuning, right? So it's not just about creating a table and using it. Okay, so now regarding the dead tuples, bloat, and vacuum. So I think we have discussed about older versions, and yeah, let me know whenever it's the time to take a break. I think it's in 5 minutes. Okay, good. Okay, so in Postgres, like we discussed about older versions, so these older versions eventually become dead tuples, right? So these are the dead tuples which needs to be cleared because these are generated upon update and delete, which we discussed. So it's a vacuum that needs to delete this space, but it's not really shrinking it, right? Vacuum is clearing the space so that the future inserts or updates can use it, right? So even in the previous case, when you run a select on a hot update, right, after a hot update, because it's clearing that space, a future update or a hot update can leverage that space, right? So vacuum clears the dead space, but can vacuum not just do that? Can vacuum also shrink it? The answer is yes. When? Assume that you have a table of a few gigabytes, which is, let's say, 100 data blocks, right? We speak in terms of blocks. Now, because of no tuning at the fill factor level, you have data unevenly distributed, completely unevenly distributed, right? For some reason, the data that you want to purge, which is as of 1 week, 1 week ago, you want to just purge that data. You ran a delete statement. Now you're deleting data from the last pages at the end of the heap, right? So where is your high water mark Your high water mark, let's say, is at the 96th block. Now, what happens is it understands that these blocks that I've picked up to clean up as part of my vacuum process do not contain any live versions. So I can happily delete those blocks, but to remove those blocks, I will go ahead and acquire an access exclusive lock on the table. This is a problem. Nobody understands why everything is piling up, right? Because what happens in an access exclusive lock? Something that everybody doesn't realize, and that is when there is a select happening, you go ahead and try to attempt for an access exclusive lock. You see that there is a select. So now you're in the queue. Now you're in the queue, but doesn't mean that you're not doing anything bad. You are actually doing something bad here by staying in the queue. And that is anything else that's coming to perform a select after this request for access exclusive lock, which is waiting, right? They start piling up. You will never be able to imagine that there is some statement which hasn't yet started, doesn't even appear active, is responsible for creating a chain of locks just because it's in the queue, right? To attempt a lock, right? And now combine all of this with the vacuum, removing the dead pages at the end of the heap by acquiring an access exclusive lock. All you would do is you will see, okay, I mean, what's really happening? Why is vacuum, which is not even doing much of a damage, waiting? And I see some select happening and I see everything piling up. Nobody in the world can really figure it out immediately, right? Unless so yeah, I mean, you can, of course, you can see the chain, you can really understand it, but these are all some of the things that require a lot of internals. So this is where you have parameters that disable this functionality. Starting from Postgres 14, you have parameters to vacuum, truncate. Yeah, all right. So let's continue now and discuss a little more about, so the common misconceptions. So we discussed that vacuum doesn't just leave the space to the operating system, and at the same time, you might have to run vacuum full or a PG repack. So vacuum full is one of the functionalities that can be used to rebuild the entire table and reclaim the space, but that acquires lock. And this is where PG repack is going to be helpful, because PG repack is going to help us rebuild the entire table almost online. So it's going to internally maintain, it's going to make a copy of the table and track the changes using some triggers, and then it's going to flush those changes and then take an exclusive lock on the table, swap the tables, drop the previous table. The only problem is when PG repack crashes in between, where you may have to do some kind of repairs, but that is also very rare. Okay, so how does vacuum get triggered? So when does vacuum run? So we discussed about stats collector background process that is tracking all the inserts, updates, and deletes that are happening to tables. Okay, now when those changes do happen, right? So, oh, I see. I hear some sounds. Sorry, was that? Okay. Yeah, sorry about that. Yeah, so what happens is whenever there are any changes that are happening to table, since the last statistics gathered time, right? So let's say, okay, assume that there are no statistics collected, it's a fresh table. Now the stats collector process is actually tracking the number of changes happening. So where is it looking at that? So let me try to show you real quick. Okay, so there is this table called or catalog view called pgstat user tables or pgstat all tables as an example. So you can probably say something like select schema name comma rel name comma number of tuples inserted, number of tuples updated, number of tuples deleted, number of tuples hot updated, right? Live tuples, dead tuples, and the total records modified since last analyze, total records inserted since last vacuum, right? When was the last vacuum time? When was the last analyze time? Auto analyze, right? Manual and auto analyze, right? So you can see all of that information about every user table, right? So you can see that if in case I go ahead and do, let's say, um, um, I will run an insert in my table, okay? And you can see the number of tuples inserted under my table changed from 2 to 3, right? And let me just go ahead and say vacuum analyze my table. And now, okay, I'm just going to go ahead and run, okay? So you can see the number of records modified since last analyze, right? And last vacuum is now reset to 0, right? Okay, so it is tracking all the changes that happened to the table until the statistics are reset, and also gathering information about how many changes happened since the last analyze and vacuum. So this is really helpful for running a vacuum. So now what happens is, we'll go back to the math real quick, right? Okay, and we see that whenever there are total number of changes, more than did tuples, I call it number of inserts plus updates plus deletes on a table that is more than 20% of the total number of records by default, right? If it's let's say the table has 1000 tuples or rows, and the number of records inserted or updated or deleted is 20%, which is 0.2 is the vacuum auto vacuum scale factor, which is 200, let's say, right? 20% of 1000 is 200, plus a threshold, which is vacuum threshold, which is set to 50, right? So in such a case, if when there are 250 changes, that's when the table becomes a candidate for auto vacuum. So we need to play with the scale factor and the threshold. Assume that there is a table which is actually, let's say that there is a table which is of 1 million records, and there is a table which is with 1000 records. So with these default vacuum settings, which is auto vacuum, vacuum scale factor, right, which is 0.2 at the entire database level, and show auto vacuum threshold, which is 50. So what it means is 0.2 times total rows plus 50, right? So if in case you have a table with 1 million records, what it means is, unless you have 200,000 plus 50 changes observed since last vacuum, the table is not candidate for a vacuum, right? But if you have a table with 1000 rows, it means if there are 250 events, 250 DMLs, it's a candidate. So this is what the distribution that we need to realize, especially when scaling, right? So what you want to do is, you want to rather go ahead and set table specific vacuum thresholds, right? So in some cases, I remember setting table specific. So I have set auto vacuum scale factor to 0 for that table only using the alter table command, right? And I've set vacuum threshold to 100,000, right? So that way I'm forcing a vacuum whenever there are 100,000 changes, right? Similar is the case with analyze. So you also have auto vacuum, analyze scale factor, and analyze threshold, right? So analyze happens a little more aggressively, 10%, but this has to be updated, and we have to fine tune it. And the number of workers is basically the auto vacuum, auto vacuum max workers, right? So 3 workers can be running at a point. I mean, do you want to increase the number of workers? But again, if you increase the number of workers, there is something called auto vacuum cost limit. When it's set to -1, it automatically defaults to vacuum cost limit 200. So on the whole, all the vacuums that are running together, even if you increase the number of workers, have a limit of 200 units. What is 200? Okay, I'm going to discuss that also. So this 200 is again calculated based on how many number of pages should be read from shared buffers versus from OS cache versus from disk. Based on that, there is a weight that is assigned for every block, right? And based on that, you will be able to go only up to, so for example, if it's read from shared buffers, right? So then how many number of units versus, so you will be able to go up to 10 MB per second if you do the math on top of 200 vacuum cost limit. When you get a chance, what I would suggest is just search auto vacuum tuning Avinash Vallarapu, my name actually speaking. Yeah, one of the very at those days, at least in 2018, it was one of the very popular article, and it still is referenced in a lot of articles, right? So you need to take a look at these parameters. So vacuum cost page hit, right? The cost of reading a page that is already in shared buffers, and the cost of hitting a page that is not in shared buffers, and the cost of actually performing vacuum on that page, right? So yeah, so based on that, you actually can see what is the cost, and that's yeah. So you take a look at this math. It's very easy to take a look at some point. Yeah. It'll just take too long. You need to tune the, and there is also a nap time. There is, there are many other parameters that you need to take a look, but just on the vacuum, unfortunately, we have to spend 4 hours at least if we have to go a little more deeper. So I just wanted to at least touch and say that you can go through that auto vacuum article that I was referring to, and it's still applicable today. Yeah. And XIT's transaction ID counter in Postgres is a 32-bit unsigned integer. So when it starts from 0, it goes up to 4.2 billion. So, and after that, the cycle again goes back to 0. So now you also have the way the older versions and newer versions are tracked in the same table, right? With transaction IDs. So now, when there is a scenario where we are at a 4.2 billion transaction ID, if in case it's 0, 0 is actually the future, right? Or 1, 2, 3, 4, this is the future. So now, should it consider 1 as a past or the future, right? So to avoid that challenge, Postgres has automatically considered half of the transaction IDs from my current transaction IDs, right, is a maximum limit allowed, right? Okay, so anything in the future is a future. For example, if my transaction ID is 100, the previous one in the cycle. Up to probably even 4.2 billion, everything else is still considered past. Up to past 2.1 billion, right? So I can go and I need to be able to consider so much as a past, right? So I mean, this again how the older versions are maintained. For that reason, if there is a reason where vacuum did not run, and some of those oldest possible transaction ID generated rows have got a transaction ID more than this half. That is called a transaction ID wraparound, because that's a future, right? And to avoid that from happening, Postgres will start warning, much upfront, 80,000 before you're left, 30,000 before it says done, I'm not allowing you to do any writes anymore. You have to open Postgres in a single user mode and perform a lot of interesting activities such as vacuum, and then that probably dates back to the way the DOS prompt used to be. I mean, you do not have interesting CLI, PSQL anymore. But again, how do we handle this? So you can look at the age of a table and see what is the oldest transaction ID versus the current transaction ID distance. What is the oldest transaction ID that inserted a record which has not been frozen? Frozen in the sense there are no changes, so there'll be a frozen transaction ID assigned to it. Yeah, so this is one of the interesting thing that needs to be monitored. And then so we so far discussed about workmem, the OOM trap, how do we avoid that, per process connection, checkpoint tuning, hot updates. So some of these, technically speaking, as part of scaling as well, checkpoint tuning, as well as sort memory optimization, as well as understanding the tuning of auto vacuum and vacuum. These are undoubtedly part of the scaling too, because if we are not thinking about these functionalities, then that is a challenge. So like I said, vacuum, when it's running, it should be able to clear the dead tuples, but it cannot clear the dead tuples if there are still older transaction IDs holding, and trying to read those, especially when the transaction state is idle in transaction, right? For example, when you go look at pgstat activity, you can see the state of connections as active, idle in transaction. What is idle in transaction? That means that a transaction actually started and the application has, let's say, issued a statement as part of that transaction. Database completed the task, sent the feedback to the application, and now database is waiting for the application to say, okay, this is my next action as part of this transaction, or commit, rollback, close connection. So application is not giving anything next, right? Any action to perform next. Now the database is waiting in that transaction. So this is the idle in transaction. And in this case, if there are any such statements that would have acquired some locks, they are still holding the locks. It could be shared, it could be even the read locks, right? Access share lock, or even any access exclusive lock, or row level lock, or any type of locks, right? So this is why it's important to monitor the long running transactions. And I think we discussed again most of this in the past. We did a great job in talking about a lot of things before we move to the future slides. So as each connection is a fork or a background process or a process, we already discussed that it is going to have certain overhead, especially when we fork and create so many processes, like forking and creating a process, dropping a process, again creating it. So this is a resource intensive task, and for this reason it is important to see how we can have a connection pooler. Technically, connection poolers, as part of the application development and design, developers generally use connection poolers, right? So it is interesting if in case there are applications that do not use connection poolers, but there is also another challenge. Now with Kubernetes and auto scaling, you have more number of application pods and several other external applications probably connecting to the database via those applications. And now each application or application pod or microservice is, let's say, attempting to maintain its own connection pool. And that connection pool, let's say, is 20 connections, 40 connections. This is where the biggest challenge with scalability is, because every application pod is requesting for, let's say, 40 connections, because I want to maintain 40 connections in the pool, because I just want to be very careful what if there is a spike. And now 40 connections are maintained, right? Those are idle connections, but they are utilizing the memory, and they're ultimately, some of these connections also, the application needs to make sure that the state management is happening correctly. What it means is, one connection is utilized, there is a transaction that ran, and that transaction, as part of that, it created some temp files, it generated some execution plans, right? So and some variables have been set. So a lot of things have happened, and that cache or the pre-cached state of that transaction should be gone when the application says, I am closing my transaction, right? I'm putting this connection back to the pool. If not, all of that memory that got accumulated because of the previous transaction is just held. So what we are basically doing is we are locking the memory with so many connections, right? This is again the case with some of these JBoss and other applications where you do not have proper connection poolers that you might want to use, right? So that is why with PG Bouncer and several other connection poolers, you have certain properties using which you can say, as an example, discard all, right? There is one of this interesting parameter that you can tell PG Bouncer or any other connection pooler to say, okay, run a discard all every time you're closing a transaction, right? Or discard only the stored execution plans, or discard only the prepared statements, or discard only something else, right? Or the temp, or discard all, by the way. So this way you are basically cleaning up the memory. But one of the things that I always get into meetings about when I speak to the application teams is I first ask how many application services are connecting to the database, right? And I take a look at the unique application names as well as the server IPs from where I'm getting connections, and how many number of connections do I see. Especially in microservices or auto scaling applications, I see, as an example, 40 connections, 40 connections, 40 connections from different IPs. So these are all the application pods that are creating those connections and just not really leveraging it. So this is where a server-side connection pooler may be helpful. It's very bad to have a connection pooler on top of a connection pooler, but we always need to prefer an application-side connection pooler. But it's still fine in some cases where you want to put such kind of a so you probably will go ahead and tell, do not always request for 100 connections or 40 connections. Rather, if you want to maintain a pool, probably maintain a pool of 2 connections or 5 connections, but rather there is someone else who is maintaining that pool for you. Not all application pods are always active. So whatever becomes active leverages that pool. So there is a pool that I rather maintain as a server-side connection pooler using PG Bouncer or some other connection pooler, right? So it's always good to see how you can, because again, if in case, even if you maintain a server-side connection pooler, if they are not adjusting their pooler settings, and if they are still attempting to maintain those 40 connections, even though only one of the connection is used, no point, because it still requests PG bouncer or any other server-side connection pooler for so many connections. So you still have to maintain that pool, right? There is no use of server-side connection pooler. The problem is PG bouncer is accepting the client request. Now the application which is requesting for a pool of connections is a client requesting for connections, right? So PG bouncer has to honor that. Yeah.
I would rather it be lower, but whatever. You go, developers.
Yeah. So that's a problem. So now PG bouncer is getting a request from the application that says, I want 40 connections, give it to me. That's it. I'm maintaining this pool. Give it to me. Right? So it has to honor that. PG bouncer can do something interesting, and that is, if it sees that there is a connection idle, unused for more than certain amount of time, probably it can disconnect it. But now the application pooler also has a setting, always maintain a pool of 40 connections. As soon as it is gone, it says, okay, I need to maintain, please give me, right? So this is a challenge that can happen. This is where I think it needs to be important to it's important to discuss with the application teams and have the very good connection management, right? Again, application teams are very aggressive, and or not, I wouldn't say aggressive, but they are always concerned about what if something goes wrong, and they want to put more limits. They say, okay, I don't want to play with this always because I need to restart my application, right? So right, so we need to be, yeah, again, with connections as well. When we have this again brings down to the point of how the load average is something that we see. For example, in the in a Linux server, as an example, when it's when we go ahead and look at a system with, let's say, 4 CPU cores, assume it's multi-threaded, 8 vCPUs. Now you have, let's say, a PG bouncer, or let's say an application trying to put 300 concurrent connections. If each of these concurrent transactions, as an example, are generally speaking a few milliseconds or microseconds, you don't even see any challenge. But assume that each of these are taking like 10 seconds each, right? Each of these transactions take 10 seconds to run some statements. So you have 8 vCPUs that are starving to accept 100 concurrent requests, which each of them run so long. So you see the load average really increasing. So what this also means is the connection pooler limits that you decide needs to be dependent on the number of vCPUs or the CPUs in the server, as well as the usual time of a transaction, the average execution time, or the time that each of these transactions take to complete. You wouldn't even imagine that in some of the systems where they were pretty aggressive in never changing the connection pool size from 100 to 10 by 10%, as soon as we reduced it, after a lot of convincing discussions, they noticed everything just going fine, right? That was a 8 vCPU system because the resources are not starving. So where is the queue is what is matters, right? So if you are putting the queue on the database server that is more of a damage compared to the queue on the application. So if the requests are rather waiting on the application because the application connection request is not accepted, that is a very minimal amount of wait because you're not starving the database server. It's just like, you know, you have 10 counters in a movie theater and you don't have a proper queue and you're letting 1,000 people just rush, right? So some lucky people do take it. It is a chaos, right? So you are only allowing, let's say, 100 people line up in a queue, 10, 10, 10, 10, and come back. And that's more of a better way of managing things. So it's just like you're letting application just say, okay, go and put every request to your database, let the database starve and eventually die, right? So how do you shift the queue from the DB server to the application server is very important, especially in the case of resource constrained environments, right? And this is where you rather, when you benchmark it, you will see better performance with limited number of connections as part of the pool. I think we already discussed about the active versus idle in transaction. I'm very happy that I'm always covering my future slides. So in the previous slide. So idle in transaction, we already discussed how that can be dangerous. And timeouts that can protect, yes. So these are interesting timeouts that can probably make you feel happy, but make application developers feel concerned that they have to start optimizing, right? So idle in transaction session timeout. So to avoid the damage of idle in transaction that we discussed, that is one of the beautiful timeouts that's available. And then transaction timeout. So, okay, you're running a transaction for too long. Sorry, that's really challenging all my vacuum and background maintenance tasks. Okay, and statement timeout, lock timeout, idle session timeout, right? So probably some applications, what they do is the state management is one way, and at the same time orphaned connections can also be possible because of driver specific challenges, right? Assume that you have some kind of a custom application which is actually just creating the connections but not really sending a feedback and stating that I'm closing the connection, right? Now those are orphaned connections too. There are keep alive and everything else that can handle up to some extent, but idle session timeout can really be supportive. Yeah, so you have a headroom for monitoring without super user to, like you can say, use, but yeah, again, reserved connections are the reserved connections that help only in the case of the challenging case of all connections being utilized, right? So we have max connection setting in Postgres, right? Sometimes I think, especially you see, I see a lot of AWS customers as well as other customers like setting max connections to 8,000, 10,000, 20,000. Yeah, it's possible. Could do that. But one of the reasons for that is because you don't want any customer to feel an outage, right? Customer happily just goes and sets that. But more than the outage, that is a challenge in terms of performance. So yeah, we have max connections, we have super user reserved connections, especially helpful for admins to say, okay, I have 3 connections that I can happily use even though all the connections are utilized out of 100. And reserved connections, again, you can get some headroom for monitoring. And yeah, we already discussed about the timeouts. Yeah, so like I said, you need a pooler. A connection pooler is required, especially it's a process-based database. I mean, every connection is a process. So connection pooler is important. And you have to um, tune so that the sum of all the pools, yeah, should not exceed max connections, but doesn't mean that you get max connections increased to 10,000. So also watch your pool, and let's discuss a little bit about connection pooler, which is PG Bouncer. So PG Bouncer is a thread-based connection pooler, right? So many clients connect to PG Bouncer, and the connection requests wait. Coming to your point, actually, you were also right in one case, right? So if you are making PG Bouncer not accept more than a certain number of connections, that is when you can accumulate and wait on the PG bouncer, correct? Right? So just correcting myself over there. Yeah. So you will be able to put some limit and say, let everything wait here, right? So, and then you are letting the remaining connections go. But if you are letting PG bouncer grow, even up to, so basically with PG bouncer, you can set settings to say how many number of connections to keep in the pool always, and how much it can grow up to, right? Like max connections. So yeah, so this helps queue clients during spikes instead of overwhelming the database, right? So your connections are held until here, but they're not hitting the DB and saying, okay, I'm just challenging you with my activities. Okay, so PG Bouncer supports session, transaction, and statement mode. So most of the times I see session being used, but PG Bouncer works amazingly great for transaction mode of pooling because the scalability is better. However, why is transaction mode sometimes not preferred is because, especially in the case of prepared transactions, people generally, developers use prepared transactions a lot, and that is because you do not have to let Postgres create an execution plan each time as well, right? One of the other interesting reasons for it. And at the same time, from development perspective, and that's a best practice to do, always using prepared transactions. And for that reason, session mode is generally used. And statement mode, it's very rare to see somebody using the statement mode in PG Bouncer because every statement is a connection, right? Every statement is a connection in the pool. So this is where, if in case you're not aware of how the application is designed and whether they're using prepared transactions, etc., go with session mode, which is at least giving you better compatibility and still queuing up. That's good enough, right? And yeah, so yeah, so one server, again, in this case, right? So assume that we have a typical fan-in ratio of 5,000 client connections, and you have a PG bouncer transaction mode, and you have 20 to 50 as the limit that you're setting as part of the pool. So even if you have max connection set to 200, still amazing, right? So this is where, even if you have microservice architecture, or you have, serverless, or any other architecture where a lot of services are connecting to the database, your PG bouncer kind of a connection pooler is able to just accept only up to a certain limit based on the configuration. Because most of the times what I also notice is that all of these microservices or etc., like, they are very short lived. At the same time, they're also not completely actively using all the concurrent connections that they assume they should, right? So yeah, again, shifting some of these workloads to, again, especially when you see some of the traffic hitting the databases for stale data or static data, it's good to move that to a cache, right? And probably Redis or Valkey and say, okay, let me rather sync that in memory engine and rather shift some of the activity to the cache layer. So again, from scalability perspective, you also need to look at the workload, because you cannot do the entire scaling only with a connection pooler. We also have to understand what type of queries are coming, on what tables do we see what type of queries, and how often is the data modified in those tables. And for example, let's say you have lots of reads that are happening from the top 10 tables, which are like 1 million reads as an example per hour compared to 1000 reads per hour on other tables. In this case, how often are these tables updated? How stale is the data? And or how static is the data? So depending on it, probably we can try to discuss with the application teams and design a strategy of moving some of these tables, specific events, to an in-memory cache. So the cache is updating the latest state of data, the fresh data, every few milliseconds or a second, as an example. And your application is directly hitting that, which can really scale, tens of thousands of read requests, like Redis or Valkey can really scale too big, right? When compared to a transactional database, which is behaving differently, especially when you're hitting so many reads concurrently. At the same time, you can also go ahead and push some of those reads to a reader, right? So yeah, so some of these things again about in transaction mode of PG bouncer, what fails, right? Advisory locks that are session specific. Yeah, for example, if you have opened a session and you have certain advisory logs that are created as part of that session, that cannot be translated or cascaded to the future transactions. And temp tables across transactions, if you are using plain prepared statements, yeah, some of these. Yeah. Okay, so let's also discuss a little bit about the arithmetic. So this PG bouncer, but similarly, any connection pooler has got almost similar parameters just with different names. So the client connection, so this is what it is. So you are allowing a queue up to 5,000 connections, right? And the default pool size is 50. Minimum pool size that always needs to be maintained is 10. And then you also can put wait times, prepared statements limit, and lifetime of a server and idle event. So you can go ahead and go set up to so much. And you also have the max client count that's set to 5,000. So we have to tune some of these so that you can limit depending on your server capacity, right? And okay, so yeah, they can go up to that default pool size and wait until 5,000, right? So yeah. Okay, so again, transaction pool, right, is generally great for scaling as long as you're able to go ahead and look at all the limitations and see that there is no challenge. But especially in transaction pooling, you may see many idle connections too, because they're all short-lived, short OLTP, right? And does not have cross-transaction state. At the same time, the cleanup also has to be at transaction level. And session pooling, yeah, so especially when you need some of these interesting functionalities like listen and notify, at the same time, like the concept of web hooks similarly, right? So you also have some GUCs that you want to persist across the session. For example, let's say you want to set work mem at the session level, and you want that to be cascaded throughout a set of transactions that are running through that session. Again, session pooling, right? And You may do hybrid by putting two PG bouncers maybe, right? Yeah. So you also have PG Cat and Odyssey. PG Pool 2 is one of the interesting alternatives, but PG Pool 2, if you would have done some benchmarks, you may see it an overkill at several times because PG bounds are extremely lightweight, undoubtedly, right? But PG Pool 2 or PG Pool, what it does is it decodes, parses the incoming statement and decides whether that's a read or a write, and can be configured to send all those reads to a standby instead. But this comes at a cost. That parsing it is at a cost. So if you do some benchmark, you'll be like, oh, let me not even think about it. But there are scenarios where it can be helpful, and at the same time, your function stored procedures, it doesn't know what to do, right? So should it even consider sending such functions and procedures to the standby? Because what if they are doing some writes internally? How does it know? It doesn't decode a function, right? It doesn't debug a function and see what is it actually doing internally. So there are certain scenarios that you need to handle manually, and pgcat is multi-threaded, right? And at the same time, Odyssey pooler is something that Odyssey as well as supervisor is something that I would suggest you to also explore. Supervisor is definitely getting a little bit of a popularity. It's from Superbase, and RDS proxy as well as yeah, RDS proxy also has got certain interesting functionalities with respect to, for RDS proxy, if I, yeah, that was a limitation long back. It's good now. Yeah, I think it is extremely flexible. Yeah, so for RDS proxy, you always used to have, I mean, this was in the initial days of RDS proxy where for every database, you need to have one RDS proxy. You cannot have one RDS proxy for multiple databases, right? Again, I assume that that has been actually solved. Is- yeah. PG Bouncer is no doubt the lightweight among everything, right? And it's extremely configurable. I would always say start with PG Bouncer. There are specific use cases where supervisor and PGCat can be helpful, but the most flexible as well as the maintained connection pooler is PG Bouncer.
Single PG bouncer only has one backend. Have 10 PG bouncers.
Yeah, when you need to scale the connection pool, that's when you start looking at PGCat and supervisor and Odyssey, right? So what? Yeah, you were saying something. What was that? Proxy SQL? Sure. Definitely, definitely, yes. Proxy SQL, yes.
I can do
Okay, good. Yeah, and all right, so high impact tuning, especially for scaling your database activity, it's also important to understand what you want to tune. So there are some of these catalog tables that you always need to look at. So always look for what do you have in PG underscore stat underscore star, right? So, oh my God, 15 minutes. So so PG underscore stat underscore star, right? So you have a lot of these statistics tables that you can always or catalog tables of views that you can always look for various different things. For example, you have PGStat progress vacuum to show you the status of a progress of a vacuum. You have PGStat activity that is actually giving you the status of all the activity of all currently connected connections. PGStat IO, PGStat database conflicts, PGStat wall receiver. I mean, there are a variety of PGStat tables or views as part of the catalog that give you pretty detailed information. But where do you start your memory? Where do you start your tuning? So firstly, shared buffers is one of the important parameter. Like I said, or we already discussed about the double buffering, right? So should it be OS cache or should it be shared buffers? How much do you want to set it to the shared buffers? What is your active data set? How much memory do you have in your system? You can start always with 25% of RAM, the default magic, right? And probably in around 2010 or so, the default magic shared buffers value used to be 8 gigabytes. I don't know how that number came from or where, but, and then it shifted to 25%. And then it can actually be more than that as long as you have enough room for everything else. Effective cache size. This is again very important parameter that people miss, right? Again, you want to set effective cache size to, let's say, 90% or 80%. What does this mean? It means that you're telling Postgres there is so much percentage of RAM available for caching indexes, right? So you do not have to assume that an index scan is bad, especially in the, I would say a few years ago, when you do not, when you wouldn't used to use SSDs, right? So an index scan is a random seek, right? And so the cost of scanning an index is considered more expensive than a sequence scan of pages. So that's when, you know, it used to take decision, okay, is it cached? Only then I'll go ahead and rather pick an index. Okay, how much is my effective cache size? So we are helping planner, the Postgres planner, in stating you can consider this. And work mem, we already discussed about work mem tuning. And maintenance work mem is the amount of memory that you are giving Postgres for certain maintenance operations like vacuum, right? As well as create index. So if you're running a create index, how is create index expected to run faster when you set more maintenance work mem? And what is maintenance work mem actually doing? It is technically holding the references or pointers to the rows that needs to be part of that maintenance. It could be create index or it could be vacuum. And we already discussed about checkpoint, but let me also tell you something that I did not tell about checkpoint. So we discussed about checkpoint timeout. We discussed about checkpoint completion timeline. We discussed about full page writes as well. But checkpoint is not just triggered by checkpoint timeout, but it can also be triggered when max wall size amount of wall segments are about to be reached. So if you have max wall size set to 1 gigabyte, and if your checkpoint timeout is set to 30 minutes, assume that Postgres is able to generate 1 gigabytes of wall segments within 5 minutes, right? Because of the activity. Checkpoint can get triggered, right? So it can be based on max wall size as well as checkpoint timeout.
I've actually wondered about max wall size. I see it everywhere on the internet. Seems to say that's something that
it does. I've set several systems where max wall size is 30 GB, 40 GB. Exactly. I want to make sure. So checkpoint timeout is not the only way of tuning checkpoint or reducing the checkpoint frequency. It's also the max wall size. That's a default. Max wall size of 1 GB is the default. That's a problem. Yeah. If it's a problem. Exactly. I mean, because we see that, right? So, yeah. Right. So, auto vacuum scale factor. We again discussed about that. The global vacuum scale factor can be great for some tables, but not all the tables. So you need to have table specific vacuum settings that needs to be tuned for scalability. And then random page cost. Okay. So if you go ahead and say random page cost, it defaults to 4, right? So in some cases that is still okay, but what you're trying to say is the cost of scanning an index page is 4 times compared to the sequence page cost, which is 1, right? So the cost of reading, I mean, especially if you're doing a full table scan, the number of pages that you're reading, right, times 1 unit is the total cost compared to the total number of pages that you need to read in the case of an index scan multiplied by 4 units per an index page. So this is where you might want to reduce the random page cost and set it to 1.1, which is what we generally set to, especially when you have faster disks. And at the same time, this is one of the reasons why there can be some of the bad plans that can be chosen by taking a deroute from index scans. And yeah, when you run and explain analyze buffers, you would be able to see some good amount of information about whether the index scans are being performed or sequence scans, right? Okay, so shared buffers, effective cache size, max wall size, work mem, random page cost, hot updates, we discussed that. We discussed about scale factor, we discussed about maintenance work mem, and extended statistics. Okay, so default statistics target in Postgres, can anybody guess this? 100, right? So what is 100 here? So default statistics target is basically nothing but the number of histogram boundaries that you need to collect. For example, assume that you have 1000 rows. When you run analyze, Postgres is collecting statistics for, Postgres is maintaining 100 histogram boundaries of statistics. So it's, okay, let me collect 1 to 10, 11 to 20, 20 to 30, the average row sizes, the average row lengths, or the most common values, etc., etc. So it's able to maintain up to 100. And if you have 1 million rows, it's still maintaining 100, right? So the planner estimate is based on the statistics always. So, but can you go ahead and maintain even more statistics? Yeah, you can, but you're, of course, bloating that stats table unless it's required. So there are scenarios where I've seen people setting default statistics target, at the table level to 1000, 2000, right? So you maintain more histogram boundaries. So this is one of the things, and extended statistics can also be used based on the combination of columns on which, depending on what type of operations happen, because you are saying that the result set is always influenced by the other column also, not only you, because you're just part of the filter condition. So you're combining and letting it decide based on the combined statistics available for a combination of columns too. So that is something that can be helpful. And let me now quickly go to the replication fundamentals. So I think we discussed about, let me see how fast I can complete this, right? So I discussed about, I think, wall sender process, which is able to also send walls, and the wall receiver, and the startup process, which is actually the replaying the wall segments in streaming replication, right? So it's byte, byte, byte. So when you have a primary, when you have a standby, you have the wall segments that are continuously streamed byte, 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 and they are actively replicated. So the key parameters for replication, wall level replica, and you can also go a little more further and say logical, but you are writing some more additional information to that helps you decode that wall logically and apply some perform logical replication. Max wall senders, so the number of wall senders, it defaults to 10 today, and even replication slots. Replication slots help you not get a wall deleted from the wall directory unless the replication slot which is active says that I've utilized it, so okay to delete it. This is generally used in the case of replication or logical replication or streaming replication. Physical replication slot or logical replication slot can be useful, but that can also create challenges by accumulating and allow maybe it can, if it's not consumed and if it's a stale replication slot, just created that way, not consumed, not it says that do not delete this wall segment even if it is 1 day old, and ultimately the wall directory is 100% full. Primary coninfo and primary slot name. So these are some of the parameters that are helpful to set up the replication. So you're telling standby where is your primary, and you're letting it create a replication slot. And the standby.signal file is created to say that yes, I'm a standby. And then you take a backup and you just start it, and it automatically brings the system back to replication. System in replication. You have synchronous commit functionality. So how many of you actually know that synchronous commit, which you set to, let's say, read write, or let's say, so you have different synchronous modes in Postgres. So you can say that a transaction is committed only when the success message that the transaction is committed is sent even by at least one of the standbys, right? So you have synchronous commit local, you also have synchronous commit remote write, right? Or remote apply, right? So what it means is another standby from a list of standbys that you're passing to synchronous standby names should acknowledge and say that yes, I have successfully received this, right? But there is another interesting challenge with Postgres. So let's say that somehow the transaction which issued that synchronous, a transaction which started by the client took some time waiting for the standby to come and give a feedback that it is committed, right? Because of some latency. Now there is a wait timeout at the application client level. Now application terminates it, assumes that the transaction never got committed. But the problem is the transaction is actually completed already on the primary, right? So it's the application that has to make sure that whenever such timeout happens, it has to go back and see, did I do it correctly? Is it a real timeout or the changes already happened? Do I need to fix it? It's unfortunate, but this is how it works, right? If you go and test it today, you will realize that. And synchronous commit, you have, like I said, you have different way, remote apply, remote write. So remote write is actually making sure that the standby is just writing the wall locally to the file system, that's enough. But remote apply is basically the standby is also replaying that and saying I've also applied that transaction, right? Local is always just to the local file system. And so to see the lag, of course you have pgstat replication, one of the interesting catalog that's available that gives you enough detail about the lag. And if you have so you have a hot standby, you have a replica, but it doesn't do the automatic failover. So that is when you need Petroni. And interestingly, we did the failover in the beginning of the exercise using Petroni. We never got a chance to see how Petroni works. Honestly speaking, for some, I think at least for a technical person like me, I cannot I do not want to really cover entire Postgres in 3 hours. So I could not really, I don't think I'll be able to do the justice by covering Petroni configuration file as well as the Petroni setup. But I just wanted to do my best to just say that, yeah, so you have the ability to perform manual failover, right? And did anybody hear about PG Rewind? Right, so PG Rewind is one of the interesting utilities when wall log hints is set to on. You do not have to rebuild the entire primary, which is now a standby, right? So after a failover or what you're doing is you're doing PGCTL promote to make a standby a primary. Now the previous primary, which has to become a standby, need not be rebuilt from scratch. We can use PG Rewind to quickly go back to the state and continue from the actual primary and stay in replication, because especially in terabytes of systems, that'll be challenging. And then, so you have RTO and RPO that really defines the high availability in general. And this is where Petroni is one of the interesting orchestrator that can be helpful. So I'll try covering Petroni in under 3 minutes if possible. Okay, so you're already on top of the hour. So Petroni, in a simple way, it's a template. It's not a high availability tool. Please consider that it is a template. It is a template that is allowing you to choose your distributed consensus store, which is storing the health of the leader and parameters and everything, right? And supporting the leader election process. And then it can also integrate with Softdog or a watchdog, basically a software watchdog, which is Softdog, to avoid split brains. So when I'm unable to get an acknowledgement that I am heard and I am accepted as available in the quorum, in that case, I'll just kill myself. And that is what the Softdog does, right? Smith, shoot myself in the head, right? And Stoneth is shoot the other node in the head, which is not what Petroni does, but Smith is what it does, right? And then it's important to have at least 3 nodes in the cluster. You do not want to have a 2-node Petroni cluster. You may have, as long as you have 3 different processes doing the leader election, etc. But yeah, I don't know why, but 3 nodes is really important, right? And so one node holds a leader key, and the leader must continue to renew its leader key every 10 seconds, right? When it stops renewing, a leader election starts. And leader election starts using, let's say if you're using etcd, interestingly it happens using that raft algorithm, and which is one of the most fantastic algorithm for leader election, which probably takes 15 minutes to discuss, but it's a very good algorithm that you can go and look at, trust me. So yeah, and then it triggers based on certain, so lead release time, as well as loop period, as well as when to retry, when there is a timeout that has to happen from a primary. And so some of these parameters can be optimized to make sure that you are being aggressive in terms of triggering a failover. So that is where you need to understand the RTO and RPO, as well as a lot of other important parameters. So max lag on failover is one of the important parameters that can actually help you understand whether you need to really let that automatic failover happen or not. So how much is the amount of data that you can lose, right? So depending on that, you're able to trigger a failover. Switchover versus failover, I don't think it really makes any difference if I talk about that, you know it, but switchover is planned, failover is unplanned. Petroni can take care of failover as well as switchover. We did a planned switchover when we started the exercise. So interestingly, we had a 3-node Petroni cluster. I'm connected to Petroni node 1, and at that time, Petroni node 1 was a standby, Petroni node 3 was a primary. So instead of spending 2 seconds to connect to the Petroni node 3 server, we did a switchover. So, and we ran some transactions. So that's what I did. So yeah. Okay, good. So the last line of defense, a split brain, is actually the watchdog. So you can add that configuration to the Petroni YAML configuration file. We already discussed about PG Rewind that can automatically rebuild a demoted master, right, without redoing the entire backup, right? So Petroni allows you to just define the wall lock hints to on, and it's internally doing PG Rewind something like this. So what it's saying is, this is the demoted master, so resynchronize yourself with the new primary, right? And in order to do that, it's not copying everything again. And Petroni also exposes certain REST APIs. So these REST APIs are very important because especially when you're using Petroni, how does application perform a transparent application failover, right? So TAF is very important. Now in this case, you can leverage Petroni's REST APIs to understand what is a primary, and you can use F5 load balancer or HA proxy kind of a load balancer, and you can put the logic in place to say that when the Petroni REST APIs returns the node status as master or writer, go ahead and redirect the write traffic. And when it says it's a reader, redirect the read traffic. So, or all connections go always to a writer node. So whichever node returns the status as a writer, redirect the connection to that. And you can have HA proxy plus PG bouncer playing the role. So your application is actually connecting to the PG bouncer, and PG bouncer is connecting to the HA proxy, and HA proxy has got the logic to always redirect by talking to the Petroni's REST API. So if you do a curl on port 8008, it says 200 when you're searching for primary. It means it's a primary, right? So sorry.
That's very nice.
Yeah. So that way, you know what is a primary.
I hadn't understood that from the docs. That's good.
Yeah. So yeah. Was that sorry? Why not using the database as a source of truth? So you are again, because Petroni is already doing that, right? Petroni is already tracking that status, but you're now establishing the connection to all the 3 databases, and especially when your database is down or the network is unreachable, you are spending time until a timeout looking at whether that database is really able to come back and give you a response.
So you have the application connecting to bouncer connecting to proxy, and well, actually, proxy checking Petroni and proxy connecting to the backend.
Correct.
What PostgreSQL does in the backend is checking directly the database, so it knows from the knows which one is valid.
That's what Petroni does, yes.
Yeah, but you're
So you're asking PostgreSQL, right? Similarly, you're asking Petroni.
collapsing together.
Understood. Yeah.
PostgreSQL failover?
So
Right, so this whole software stack is 4 pieces acting together, and yours is 2.
yeah, you're also taking care of the load balancing, the TCP/IP, whatever HA proxy is implementing. Are you doing that? Okay, great, which is good, which is good. But the only thing is, again, the failover is an action that has to be performed too, right? So that's probably the only thing. Yeah, I mean, no problem. Yeah, so consensus, promote or no promote, watchdog for fencing, and REST API to note the status. I mean, general Petroni setups have such kind of an architecture, right? HA proxy. PG bouncer is an optional, right? So you probably have HA proxy plus PG Petroni, because PG bouncer is only in the case where the application connection pooler is not smart enough, right? So you have an application directly connecting to HA proxy, which is reading the state of the clusters using the Petroni REST API. That's it. So you can still make it two, only in the case where the application's connection pooler is not smart enough. That's when PostgreSQL as well as PG bouncer come in picture, right? Yeah. Okay. Yeah. So this is where I think yeah. So I just want to show this configuration file. So what's happening is in HA proxy, you're saying for your writes, go to port 5000, for your reads go to 5001. And what is 5000, right? Basically, do an HTTP check and see which one returns the status 200 when you're looking for primary, right? And here, do a check and see which one is returning status 200 as a replica. And automatically 5000 will always go to whichever node returns 200, right, as a primary. So yeah, you are also implementing some amount of load balancing, like round robin for reads. So yeah, this is about HA proxy, just in case I wanted to add, right? Yeah, I leave it to you to decide what to do, what to use. Yes. I think we're good. This is all, yeah. Observability, I think, yeah, I don't think you really need to. Yeah, connection pooler, look at the PG stat activity. We covered all of this. We did a great job in covering a lot of these things in the beginning itself. Done. 86, 87, 88. Thank you. Yes.